So to prove that certain random variables are independent, we have to prove that the corresponding event in the sigma algebra of those random variables are independent. So let me repeat, to prove x1, a random variable, and x2, another random variables, are independent, we need to prove that any event coming from the sigma algebra of random variable x1 and sigma algebra A2, another event coming from the sigma algebra of x2, are independent. Here I use the symbol for the independence, which is from some other node, and I previously used this one, which is not the symbol for the independence. This is usually the symbol for the this perpendicular or orthogonal. So let me correct. So this is the symbol for the independence that I'm going to use. So looks like we have to check for all the sets, all the events. We have to check for all the events for all events A1 and A2 within the sigma algebra. But as in the most case before, we don't have to check for all the events in the sigma algebra. We only have to check for all the events that forms the pi subset of the sigma algebra. So let me state that. So the theorem is the two sigma algebras are independent only if their pi subsystem that generates each sigma algebra is independent. And let's call this pi subsigma algebra pi system, which is also subsigma algebra, sub pi system that generates the sigma algebra F1. So let me call them beautiful P and beautiful P2. So here definition is P1 is the pi system that generates the sigma algebra F1. Of course, P2 will be the pi system that generates the sigma algebra F2. So if you show the independence of any element in this pi system, then it means that the sigma algebra is also independent. We don't have to check all the elements in the sigma algebra. It's enough to just check the independence for the pi subsystem of the sigma algebras. Proof is again Dynkin's pi lambda lemma. So let me review what is the Dynkin's pi lambda lemma. You have to remember what is the Dynkin's pi lambda lemma. And after this course, I really want you can state what is the Dynkin's pi lambda lemma. So to do that, we have to know the definition of pi system. Pi system, the definition was closed under intersection. The definition of lambda system was more involved. The definition of lambda system is about monotonic sequence, always for the monotonic sequence. So first, the full set must be there, or the empty set must be there. And but that's trivial to check usually. But important part is if there are two sets, one belong to the other. So let's say event A and B, one A is belong to B. When if both are lambda system, then B minus A is also in the lambda system. The second property is that if there's an event which is monotonic, event that's monotonic, A1 belongs to A2, belongs to A3, and so on, then the union of all the events is in lambda system. So that's the defining property. Of course, there's another condition which says the full set must be in the lambda system. So with this definition, the pi lambda lemma states the following. Let curly P a collection of events that forms a pi system. Then we can define lambda of P to be smallest lambda system that contains this curly P. then the pi lambda lemma says that this is actually the smallest sigma algebra that contains the pi system. Okay, now let's prove the theorem. So we define P1 and P2 to be a certain pi system that generates this curly F1 and curly F2. So this is our assumption in the problem, assumption in the theorem. Okay, now let's pick certain event from pi 2. So A2, let's say it's an element of P2. And let L be all the events in curly F1 that is independent with A2. Also here, this is space is all based on single sample space. So we consider there's a probability triple, omega and sigma algebra, which F1 and F2 are both sub-sigma algebra of this F without subscript. And the probability is also, probability measure is also defined, because otherwise you cannot define the independence. So we are assuming this probability triple as a background. So we find all the events, which is an element of curly F, such that A is independent with A2, which means this equation, probability of the A intersection A2 is equal to the product of probability of A and probability of A2. Then we can prove that this collection curly L is a lambda system, because if A is the full set omega, then the equation is trivially true. You can check. And if it contains two events A and B that belongs to curly F, then you can also show that B minus A is in this system. And here what we have to use is the only property, the only non-trivial property of the probability measure, which is the countable additivity. And the last property is also, of course, the result of this countable additivity, but you can also prove the intermediate result with using the countable additivity. You can prove the continuity of the probability measure, and using the continuity of the probability measure, you can also show if there's a monotonic sequence of events, A1 belongs to A2, A2 belongs to A3, and so on, then the whole union must also satisfy the same equation. Therefore, it's in this space curly L. So after checking those things, you can check this is a lambda system. Therefore, curly L is a lambda system. So it's of course containing the smallest lambda system. That before applying the pi lambda lemma, we have to use the fact that it's this curly L is also containing the pi system. So where does it coming from? So in the theorem, we assume that curly P and curly P1 and curly P2 is independent, which means if A belongs to curly P1, then then automatically the event A will be independent with A2, because A2 belongs to curly P2. And by definition, any event in curly P1 is independent with any event in curly P2. And this means that this whole P1 belongs to this curly L. So curly L is indeed containing this pi system P1, and it's a lambda system. Therefore, this curly L must include the smallest sigma lambda system that contains P1 and the smallest sigma algebra that contains P1. So it contains curly F1, which means that any element in curly F1 is independent with A2. F1, any element in F1 is independent with A2. And A2 was an arbitrary element in P2, curly P2, which means F1 is independent with curly P2. To prove that curly F1 is independent with the whole curly F2, then we have to do repeat the same argument once again by choosing A1 to be any element in curly F1, and then defining this curly L to be all the events that are independent with A1 now. So repeating the same argument as above. Then you do the same argument to show that this new definition of curly L is also a pi system and the lambda system, and that contains curly P2, and therefore L must include the sigma algebra of curly P2, which is F2, and that shows that any element in F1 is independent with any element in F2. So that's proving the final independence between these two sigma algebra. So the second step, I sort of did it much quicker, but this obtaining, if you understand the full step up to this part, obtaining the F1 is independent to P2, then the second part is just the repetition of the same steps. Such theorem is useful to prove the following very useful theorem that we will going to use all the time. So if there's a sequence of function fi which are Borel measurable functions, so I can be those numbers, positive numbers, then you can consider independent random variable also x1, x2, xr independent. So assume that they are all independent random variable. Then it follows that if I apply to xj, those are also random variable. We show that given a random variable, its composition with any Borel measurable function is also random variable. Moreover, those random variables are also independent. So given a random variable, any function applied to them is also random variable. So for example, if x1, x2, x3, those are random variable, independent random variable, then x2 to the square, x2 to the square, x3 to the square, those are also independent random variables. So proof is quite short and direct, but you have to remember what's the meaning of the independence. Independence means that the sigma algebra for x1, sigma algebra for x2, those are independent, right? That's the meaning of the random variables being independent. And here we have to show that this new random variable, f1, x2, those are independent. So we have to show that the sigma algebra of f1, x1, sigma algebra of f2, x2, those are independent. That's what we want to show. These are want to show. But what you can easily show is the following. You can show that the sigma algebra of f1, x1 is actually a sub-sigma algebra of this one. So, and that's the end of the proof, because sigma algebra x1, they are already independent, and any sub-sigma algebra will also be independent with all the others. And the proof of this one is coming from this sigma algebra in a different way of writing it. So it's the set of all the pre-image of Borel sets. So for where the B is any element in the Borel set. So that's the explicit expression of the sigma algebra, and therefore the right hand side will be pre-image. It's a composition of x1 and f1, so you have to take the pre-image of under f1 and then followed by the pre-image of x1 of the Borel set for any Borel sigma algebra. How to show that the left one belongs to the right one? That's because this part, which is the pre-image of a Borel set, is also a Borel set. It's a Borel set because f1 is Borel measurable. That's the definition. The pre-image of Borel set is a Borel, which is exactly what it means, that f1 is a Borel measurable, and therefore the left-hand side is also an element of the right-hand side.